We've been investigating the relationship between two variables. So far, we looked at the relationship between two categorical variables, either nominal or ordinal variables. Today, we're going to start looking at the relationship between two continuous variables, either interval or ratio variables. Think back to the beginning of the course. We looked at an example of exam scores. Some exam scores were high and some exam scores were low. Is there anything we can do to explain why some scores are high and some are low? Well, if we have more information, we might be able to use that information to explain why some exam scores are high or some are low. Suppose we know about studying time. We can plot the two variables together, and we find that people who don't study very often also tend to have very low exam scores, and people who study a lot tend to have high exam scores. At the beginning of the course, we asked two questions. What is a typical observation like, and how similar are observations? Suppose we wanted to predict how many repetitions a University of Georgia woman athlete could do at 70 pounds. What would be a reasonable prediction? What is a typical observation like? In the absence of any further information about an athlete, we could predict the number of repetitions using the mean of all athletes, 15.125 repetitions. Since the mean is a measure of central tendency, or a description of what a typical observation is like. Now, what if we wanted to know how good this prediction is? How similar are the observations? The standard deviation, 8.85, is a measure of variability, or how similar the observations are. The standard deviation also tells us how much error we would have on average if we predicted a student athlete's repetition 70 using the overall mean. What if we wanted to do better? Perhaps like the exam scores, we could use other information about the athletes to improve our prediction. Earlier in the semester, we looked at the relationship between repetitions 70 and repetitions 55. We found that athletes who were low on repetitions 55, say 10, tended to be lower on repetition 70, somewhere between 0 and 8. And athletes who were high on repetitions 55, say 40, tended to be higher on repetition 70, say between 20 and 30. When having a certain value on one variable changes how likely your value on another variable is, we say that the two variables are associated, and if the association is linear, we say that the two variables are correlated. So we're interested in reducing the prediction error when predicting repetition 70. If we know repetitions 55 and we know that repetitions 55 and repetitions 70 are correlated, how could we use what we know about repetitions 55 and repetitions 70 to improve our prediction? Instead of using the overall mean to predict rep 70, we can use the conditional mean. That is, we find the mean only of athletes who have the same reps 55 and predict using that mean instead of the overall mean. For example, if reps 55 is 10, we might predict something like 3 for rep 70. But if reps 55 is 40, we might predict something like 25. When we use the conditional mean instead of the overall mean, what happens to the prediction error? The standard deviation decreases. Compare the length of the red bars with the whole range. Athletes who have the same reps 55 are more like one another than they are like all athletes. So we seem to have achieved our goal of reducing the prediction error. How can we make this logic more precise? We can use the equation y equals mx plus b to describe a line. The linear equation relates to these two variables exactly. If you know the value of one variable, the linear equation tells you exactly the value of the other variable. But that isn't quite what we want. If we know the value of reps 55, we don't know exactly the value of rep 70, but we know generally the value of rep 70. We can use the linear equation as the basis of a model for the relationship between reps 55 and rep 70. A regression model is a model of the linear association between two variables, whereby the conditional mean of one variable, given the value of some other variable, is described by a linear equation, y equals mx plus b. And the standard deviation of the conditional normal distributions of the outcome variable is constant, irrespective of the value of the explanatory variable. So we have a model that gives us a distribution for the values of y, and we have a separate distribution for each possible value of x. The mean for these distributions is given by the equation y equals mx plus b, and all of these distributions have the same standard deviation. So for example, with reps 70 and reps 55, we find the regression equation y equals 0.78x minus 5.5 with a standard deviation of 3.15. So this regression equation gives us the mean for rep 70 at each value of reps 55, and the standard deviation is going to be the same across the board. So when reps 55 is 10, the mean for rep 70 is 2.3, and the standard deviation is 3.15. When reps 55 is 20, the mean for rep 70 is 10.1, and the standard deviation is 3.15. When reps 55 is 30, the mean for rep 70 is 17.9, and the standard deviation is 3.15. And when reps 55 is 40, the mean for rep 70 is 25.7. And what's that standard deviation? Oh yeah, it's 3.15. Think back to our discussion of categorical association last time. What did we mean when we said that two variables were independent? Two variables were independent if having a certain value on one variable didn't change your chances of having a given value on the other variable. The two variables had nothing to do with one another. To investigate categorical association, we made a contingency table with the conditional proportions of one variable given the value of the other variable. That is, we said, what are the proportions of each kind of happiness just for people with above average income? And what are the proportions of each kind of happiness just for people who have average income, and so forth. Looking at the table of conditional proportions, we could tell that the two variables were independent if the conditional proportions were the same for each row. Each set of conditional proportions, the rows of the contingency table, was a conditional distribution for the happiness variable. And if the two variables were independent, then all the conditional distributions were the same. No matter what level of income you had the same conditional distribution of happiness if they were independent. In regression, we have conditional distributions as well. We write a conditional distribution for the outcome variable y conditional on the predictor variable x. All those conditional distributions have the same standard deviation, but the mean for each conditional distribution comes from the linear equation, y equals mx plus b. What would independence look like in a regression? Independence means the value of one variable doesn't affect the distribution of the other variable. So no matter what value you have for your predictor variable x, you'll have the same distribution for the outcome variable y. If all the conditional distributions are the same, then they must have the same mean. Since the means come from the linear equation must show the same value for y, no matter which value you plug in for x. What does that line look like? It's completely flat, a horizontal line. The slope for this line is 0, since there's no change in y for any change in x. So in regression, two variables are independent when the linear equation has a slope of 0, because that's when the mean for each conditional distribution of the outcome variable y is the same, no matter the value of x. Now, when we were dealing with categorical association, we couldn't simply look at the conditional proportions for a sample to see if they were the same. Each time we draw a sample, the sample proportions are going to be close to the population proportions, but they won't be exactly the population proportions. Even if the population conditional proportions are the same because the two categorical variables are independent, the sample conditional proportions are likely going to be just a little different due to the sampling variability. Instead of looking at the sample conditional proportions directly, we had to conduct a statistical test to determine whether it would be unusual to have such different conditional proportions if the two variables really were independent. Similarly, in regression, to determine whether two variables are correlated, we want to know if the slope of the linear equation is equal to 0 in the population, but we only have data for a sample. We calculate the estimated slope based on that sample. Like all statistics, this estimated slope is going to vary somewhat from study to study. The estimated slope will be close to the population value, but it's not going to be exactly the population slope. So to investigate whether two continuous variables are associated, we have to conduct a statistical test to see if our sample slope suggests that we have evidence that the population slope is different from 0. So let's jump into it with the assumptions of a test of a slope for linear regression. Our first assumption is that we can use a linear equation to describe the association between the two variables. Second, as always, we have to have randomization. And third, the population of y for each value of x has to have a normal distribution with the same standard deviation for each value of x. Next, we have our hypotheses. Our null hypothesis is that the slope is 0, and the alternative hypothesis is that the slope is not 0. Here, we're going to use the Greek letter beta to represent the population slope. And now for our test statistic. Just like before, we're going to take our estimated slope, here I've written it as beta hat, and subtract the null hypothesis value, which is 0. Technically, we don't have to subtract 0 because that doesn't actually change anything. So we could have just written beta hat, but I wanted to emphasize that we're taking the difference between what we expected under the null hypothesis, 0, and what we actually got, our estimated slope. So we take that difference and we divide by the standard error. We're going to use software to find the slope and the standard error, so we won't have to calculate those by hand. Once we have our test statistic, in order to find the p-value, we need to know the sampling distribution for the test statistic. This test statistic has a t-distribution, and the number of degrees of freedom is n minus 2. That's the sample size minus 2. We subtract 2 because we have to estimate a slope and an intercept to get the regression equation. That's two things that we have to estimate, so we'll subtract 2 from our sample size when we're finding the degrees of freedom. Okay, let's look at an example. One measure of physical strength is the maximum weight that a person can bench press. But it can be dangerous to press the limits to find this maximum weight. Finding the number of repetitions someone can do at 60 pounds is much safer. So if the number of repetitions at 60 pounds is correlated with the maximum weight that someone can bench press, we could use the number of repetitions at 60 pounds, which is much safer, to predict a person's maximum bench press weight, which is what we're interested in, but is kind of dangerous. A physical trainer measured the number of repetitions his clients could do at 60 pounds, and then very carefully figured out the maximum weight that they could bench press. This computer output shows the information necessary to conduct a test of a slope. There's a line in this table for the intercept and another line for the slope. The slope here is listed as BP60, which was the name of the variable used for the number of repetitions that each person could do at 60 pounds. The coef column, that's short for coefficient, lists the estimated value for each given parameter. So the coef column in the intercept row gives us the intercept, and the coef column for the BP60 row gives us the slope for BP60. So then the estimated regression equation is the maximum bench press weight equals 64.5, that's the intercept, plus 1.49, the slope, times the number of repetitions at 60 pounds. The computer output also gives the standard error for each estimate, so we don't have to calculate that by hand. Here, we're only interested in the standard error for the slope, which is 0.150. Very helpfully, the computer has also calculated the test statistic t for us as well. The test statistic was found by taking the estimate and dividing by the standard error. That gives us 9.96. There were 57 athletes in this sample, so the test statistic has a t-distribution with 55 degrees of freedom. That's the sample size minus 2. This test statistic, 9.96, is really large, so the p-value is going to be very, very small. The computer listed 0.000 for the p-value of this test, but the p-value isn't actually 0. It isn't possible for a p-value to be 0. There's always some small chance that your sample statistic is very far away from what you were expecting under the null hypothesis, even if the null hypothesis is true. Listing 0.000 is just computer speak for less than 0.001. So our p-value is less than 0.001, and we have strong statistical evidence to suggest that the number of repetitions someone can do at 60 pounds is correlated with the maximum weight that they can bench press. This is good news for safe physical training. The computer output also lists r squared equals 64.3%. Recall that r squared gives us the proportional reduction in the prediction error when we use the regression equation instead of the overall mean for our predictions. 64% is pretty good, so we can make a much better prediction of the maximum weight someone can bench press if we know how many repetitions they can do at 60 pounds.